We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
You're looking at live footage of an Ariane 5 rocket in Kourou, French Guiana. At the very top of that extraordinary machine, one of the largest rockets in the world, we find the most ambitious space observatory ever built, the James Webb Space Telescope. And today is launch day. From all of the people all around the world working on today's launch, good morning, bonjour, buenos dias. This is live coverage of the historic launch of the James Webb Space Telescope. I'm Michelle Thaler, speaking to you from NASA's Goddard Space Flight Center in Greenbelt, Maryland. And I am very excited to be with you today. Today, the James Webb Space Telescope begins its journey to explore the edge of our observable universe, and its journey into history as well. This launch has been years in the making, and the world has turned out to watch. We'll have a lot to discuss both before and after launch, but let me set the scene for what's going on around us. While I'll be anchoring coverage from here at NASA Goddard, the big stuff happens today here, at the Centre Spatial Guyanais, the Guiana Space Centre in French Guiana. This is the main launch site for the European Space Agency, a close partner in this once-in-a-generation mission, and the home of all Ariane launches. Katie Haswell is there at the launch facility and joins me now live via satellite. Okay, how are things in Kourou, Katie?
Michelle, things are looking really good. The boards are green, the mission controllers are focusing hard. We are go for launch. We've had our eye on the weather the last couple of days. The weather's been a little bit inclement, so we're keeping an eye on that. But otherwise, everything's looking absolutely great. And I have to tell you, there is just such a buzz of excitement here in the Mission Control Center. It's a remarkable feeling. Right now we're topping up the tanks on the upper stage of the vehicle. So we've got two great big arms called cryogenic arms, and they clamp onto the upper stage and they pump in the cryogenic fuel, which has to be kept very, very cold. So it has to be topped up right until the last minute because it can evaporate. You'll see those arms kind of falling away just before launch in the last couple of seconds. So up here in the Sky booth in the Mission Control Center, we have NASA's Rob Navius and the European Space Agency's Luce Fabregat. They're standing by, hi guys, standing by to take on the commentary when we get to about 15 minutes to launch. But right now, Michelle, all the boards are green. We're go for launch. Back to you, Michelle.
We'll be coming back to Katie for the final phases of the countdown in just a little bit. So I'm an astronomer, and this launch is a huge deal for me. I am personally really, really excited. But why is this such a big event for everyone? The Webb Telescope is nothing less than humanity's next effort to move closer to understanding some of the biggest questions about the origin of our universe. And it's not just the origins of distant stars and galaxies, but it's the story of us, you and me, how we got here. And speaking of questions, we'd like to include yours in this historic event. On whatever platform you're watching our coverage, drop your questions with the hashtag AskNASA. Later in the broadcast, we'll answer some of them live on air. It can't be said enough that this is a mission for anyone who's ever looked up at the night sky and wonder. People all over the world are sending in their best wishes for the success of Webb. And let's look at some of them now.
제임스 웹 우주만환경 행운을 빕니다.
Boa sorte. Webকে অনেক অনেক শুভকামনা.
Veel succes, Webb.
بالتوفيق لويب.
kongo inorimasu, Webb.
हार्दिक शुभकामनाएं.
We're still on track for a launch at 7:20 a.m. Eastern U.S. time. 2 days ago, the rocket rolled out to its launch pad in Kourou. Of course, there's already been a lot of activity at the launch site. Primary fueling procedures were completed early this morning, preparing the giant Ariane 5 rocket for flight. Let's watch this scene for a moment. We know the world is watching. Today, humanity begins its next bold adventure to extend ourselves out into the cosmos. This is something we do as a whole planet, all of us together. Befitting the global importance of this initiative, let's review some of the basic facts about the observatory shared by people all over the world who are looking forward to the Webb mission.
The entire world is looking forward to the launch of the James Webb Space Telescope. Let's hear more from a people around the globe about what makes Webb a scientific and technological marvel.
Será el próximo y principal observatorio espacial para los astrónomos de todo el mundo y llevará más allá los prometedores descubrimientos del telescopio espacial Hubble.
它是一个由美国国家航空航天局、欧洲空间局和加拿大空间局开展的国际合作项目。
Ni darubini kubwa zaidi kuwahi kuwekwa angani na ina nguvu mara 100 kuliko Hubble.
Webb is zo groot dat deze in origami-stijl moet worden opgevouwen om in de raket te passen. Om vervolgens in de ruimte als een transformer te worden uitgeklapt.
Les 5 couches de son écran solaire le protégeront du rayonnement infrarouge émis par le Soleil, la Terre et la Lune. C'est un peu comme avoir une crème solaire avec un FPS de 1 million.
अभूतपूर्व इंफ्रारेड सेंसिटिविटी के साथ ये पिछले 13.5 अरब साल तक के समय में बिग बैंग के बाद सबसे पहले पैदा हुई गैलेक्सियों को देखेगी.
در فاصله 1.5 میلیون کیلومتری از زمین به دور خورشید خواهد گشت، در حالی که تلسکوپ هابل در فاصله 560 کیلومتری از زمین در مدار زمین قرار دارد.
Thousands of people all over the world have worked for years to get us to today's launch. The core partners, NASA, the European Space Agency, and the Canadian Space Agency are the principal players. But a vast core of engineers, scientists, private companies, and more have had a hand in building this one-of-a-kind scientific platform. Without a doubt, this is the most complex spacecraft ever built, with revolutionary technologies, daring mission goals, and a whole lot of personal passion and commitment. We'll hear from our partners later in the broadcast, but first, let's hear from someone representing the science community with a rare perspective about space exploration.
Hello, I'm ESA astronaut Matthias Maurer, currently living and working on the International Space Station ISS. I'm very excited to follow the James Webb Space Telescope's launch with you all from space. Even with the naked eye, we astronauts see that the stars are incredibly sharp and brilliant once we are outside the Earth's atmosphere. James Webb Space Telescope will be the largest and the most powerful telescope in space yet. And it was built to study the big questions. Questions like, where do we come from? How did galaxies form, like our Milky Way? How are stars and planets born, like the Sun and the Earth? Might there even be life on other planets? The James Webb Space Telescope is a joint project between NASA, the European and the Canadian space agencies, and by tens of thousands of people with origins in many countries. And it will be used by scientists everywhere on Earth.
NASA Goddard is the home of the Webb Telescope, with big sections designed and built here. But actual mission operations take place here. This is the Mission Operations Center, or MOC, at the Space Telescope Science Institute in Baltimore. After launch, this facility will command and control Webb for the duration of the mission. We'll be looking at the MOC at key moments throughout the broadcast, and this will become a familiar location for viewers in the weeks ahead as the Webb team begins to set up the telescope for work in space. So as we move closer to launch, we'll actually keep a picture of the launch facility right here on the screen. But for the next 10 minutes or so, we're going to talk about some of Webb's principal science goals. If you've ever seen a telescope before, I'm certain it didn't look like this. Of course, the look of this particular machine is a direct result of the scientific questions it's been built to pursue. So fortunately, we've got an expert pair of guests with me this morning to help explain those science goals and much more. So I'm joined now on the set by NASA's Deputy Project Scientist for Exoplanet Science, Nicole Colon, and also with Macarena Garcia-Marin, the Instrument and Calibration Scientist for Webb's MIRI instrument from the European Space Agency. So welcome to you both.
Thank you. Good morning.
Thank you.
So this is our chance to kind of step back and talk about the science goals of Webb. You know, this is the part that really excites astronomers, like all of us. And I know that there's unusual things about it being an infrared telescope. There are specific science goals, infrared answers. So maybe you could start us out, Nicole, with you're an expert on exoplanets. How is the infrared really important for your study?
Sure. Well, with exoplanets, we want to study their atmospheres. And as a reminder, exoplanets are planets that orbit distant stars. So we're looking for very small signals when we study their atmospheres. And Webb is this giant telescope that we're able to use to collect these small signals and look for infrared signatures, chemical signatures of water and methane and carbon dioxide, those types of molecules in their atmospheres. And why the infrared? You know, that's really because those signatures are the strongest in the infrared. We know that they exist there, and so that's why we want to use Webb to look there.
It seems an amazing idea. So exoplanets, planets around other stars, are light years away from us, tremendously distant. So how do we know if it's water, methane? I mean, how can we probe an atmosphere so far away?
Well, with Webb, there's a couple different ways, but one of the main ways is actually using the transit technique. And this is an indirect method where we actually detect the decrease in starlight that happens as a planet goes in front of its star. But then imagine the planet has an atmosphere. Well, there's an additional decrease in the starlight because the atmosphere blocks some light from our point of view. And why it blocks the light is because there's usually a molecule or something in there like water and methane, like I mentioned, that is acting as an absorber and blocking the light from our telescope, in this case, Webb.
So going from the relatively nearby stars and planets, Macarena, you're an expert on very distant things, distant galaxies. So how does infrared contribute to your field of study?
So with Webb, we're going to be able to observe the very first galaxies and stars. We're talking about 3.5 billion years ago, so it's really mind-blowing if you think about it. And why infrared? Well, those galaxies emitted their visible light many, many millions of years ago, and that light travels towards us in time, and at the same time, the universe expands. So in that process of travel and expansion, the light shifted from the visible to the infrared, and so Webb will be able to actually observe those very original primeval galaxies. And not only those, but it will also allow us to observe everything in between so we can understand the evolution of our galaxies from the first ones to the ones we see today.
This is something kind of amazing. So our eyes interpret different energies of light as different colors. Exactly. And infrared light is a color that our eyes are not sensitive to. But like you said, it's actually just the space of the universe stretching out the light and changing it from visible light into infrared.
Into infrared, exactly.
So how are these first galaxies different from galaxies today?
Well, when you look at the images we have of the oldest galaxies we've seen, they look like fluffier and clumpier. We know they have a lot of star formation, so that they are actually, that's a really good signature to measure them. And they are like little seeds that afterwards they merged and got together and evolved until the ones we see today, which are like spirals and elliptical galaxies.
So from the near universe to the far, one of the things that infrared is very good is seeing through dust. That's another huge advantage. Maybe Nicole, could you sort of take us through that story?
Sure. With dust, first there's a lot of dust in the universe, but how stars and planets form in the first place, they are forming in these very dense clouds of gas and dust that come together, and it's very difficult to see through them with normal visible light. And so the infrared is actually able to see through that, almost like an X-ray, sees your bones, sees through our skin. You can use the telescope like Webb to see through the dust and see the inner stars forming, or see some newly formed planets that are also very warm from having just formed.
And there's even a possibility of seeing some of the very first stars, or at least some evidence of the first stars that might have existed. But could you tell us a little bit about that, Macarena?
Yeah, so the very first stars, they form right around the time of the very first galaxies, even before that. And so we'll be able to measure them, maybe not the very first one, but the first population of stars, which is really interesting because they were formed out of a very pristine material. And then from there, they evolved into more evolved stars that created all the elements we know today, things like gold, platinum, carbon, everything. Us were formed out of those original stars. So it's a really amazing adventure to observe all these objects and understand them better.
There's so many wonders in the universe, and one of the things that I would never have believed was real unless I'd seen it, the data with my own eyes, is the TRAPPIST-1 system. And that this is actually going to be one of the targets for Webb, is that right? Tell us a little bit about TRAPPIST.
Sure. TRAPPIST-1 is, like you said, it's going to be a target. There's 7 planets in the system, and they're all small, around the size of Earth, actually. So it's also a very compact system. So it's not just that there's a lot of planets and that Webb's going to observe every single one of them, but it's the compact nature that's just really fascinating, because the entire orbit of the planetary systems, like all 7 planets, they fit inside our orbit of Mercury around the sun, and Mercury is our closest planet to the sun. So imagine 7 planets in there, and there's a lot going on, but it's very exciting because we'll get to learn and do comparative science and see, are all these planets, do they have the same chemical signatures in their atmosphere? Do they all have same amount of water, carbon dioxide, things like that?
Well, thank you so much. We're going to be back to talk to you more, but thank you for joining me.
Thank you.
Thank you.
Okay. So we'll be back in some more minutes to talk with them. And remember that we're taking your questions, so use the hashtag AskNASA. Webb looks like nothing that's come before because it's pursuing scientific goals like none that have come before. It's taken years to prepare it for flight, and as you might imagine, plans of this scope and scale inevitably run into unexpected challenges. Along the way, just like any of us, it encountered things like snowstorms in the east, wildfires in California, hurricanes that deluged Houston, Texas, and of course, the global COVID-19 pandemic, which added its own profound challenges to the whole team. This story really warrants a recap, so check this out.
The Webb Space Telescope presented many engineering challenges, but engineering hasn't been the only obstacle the team had to overcome. In 2011, an outbreak of tornadoes cut electricity to the Marshall Space Flight Center in Alabama for nearly a week, while the team rushed to finish cryogenic testing on the primary mirror segments using power from diesel generators. Engineers had to endure a large snowstorm, known locally as Snowmageddon, while testing the Integrated Science Instrument Module at the Goddard Space Flight Center. And of course, everyone has had to contend with the global pandemic. One particularly memorable challenge was working through Hurricane Harvey in 2017. This massive cyclone dumped 40 to 60 inches of rain across the Houston area over a 4-day period, causing catastrophic flooding and $125 billion of damage, all while the telescope was undergoing cryogenic testing at NASA's Johnson Space Center. Though the telescope remained safe inside the test chamber, water leaked through the ceilings, people had to cover workstations in plastic tarps, food was in short supply, and a few team members trapped by floodwaters had to be rescued by boat. It was rough, to say the least, but the team and the telescope survived the storm. Despite winds and snow and endless rain, the team got it done, and Webb is now ready for its final journey atop a rocket into space.
While the Webb Telescope is a technological marvel, everything here began with questions. Questions about how the first stars and galaxies came to be. Questions about whether planets around other stars might have environments that can sustain life. And of course, the promise of discoveries we can't even predict yet. A few days ago, I had a chance to speak with someone who's probably the best person on Earth to help us understand what we know, what we don't know, and how Webb will help fill in those gaps. Dr. John Mather is a Nobel Prize winner who measured the Big Bang with an observatory built here at NASA Goddard. John is Webb's senior project scientist, and we're so pleased to have you here today, John.
Good to be here with you, Michelle.
So to start this incredible story of Webb, let's start with something that's deceptively simple, gravity. There's something special about gravity.
Gravity is special. Gravity always pulls. It's the only force of nature that always pulls. So that's special. And what makes that special is that gravity, although it's very weak, is very long range. It can reach across the universe and slow down the expansion of the material that came from the Big Bang, turn it around, pull it back together, turn it into galaxies and stars and eventually planets and a place where we could live. So that's what makes gravity special among all the forces of nature.
And something so simple, like just the idea that it's always pulling together, that simplicity leads to wonderful complexity, doesn't it?
Yes, because it's always pulling, it's possible for gravitational energy to be converted into kinetic energy, that's just heat, and the universe becomes self-heating, which is not something the other forces could do all by themselves. Clouds of gas can be compressed by the gravity until they get big enough and hot enough to light up and have the nuclear reactions inside that turn hydrogen and helium into the chemical elements you see around you, here in the house, here on the set. So carbon, oxygen, nitrogen, everything we have that we think of as ordinary came from inside stars. So we are stardust, as Carl Sagan told us, but there wasn't any stardust in the Big Bang. So we need this part of the story to be figured out. How did we come to be able to live here on our little planet when the universe started out without all of these goody things?
So you mentioned these planets around other stars. So we're almost sort of going through all these amazing science goals of the Webb. What can Webb tell us about planets around other stars?
Well, once in a while, a planet goes in front of the star, and some of the starlight goes through the atmosphere of the planet, if it has an atmosphere, on its way to the telescope. We will spread out that light into a spectrum, or what you would call a rainbow, and we'll analyze it to see what are the chemicals that are in that atmosphere. So we will be able to tell you, maybe, that's the plan, whether those little planets that might be like Earth actually could have, for instance, water in their atmosphere, and maybe enough water so there could be a liquid ocean under that atmosphere. One of the great questions. So we know they're planets. We know when we should look. We just don't know what we're going to see.
So after the Webb launches, one of my dreams is I'm going to be standing outside in my backyard and point to a star and say there's a planet around that star that we know has water vapor, oxygen, perhaps methane, carbon dioxide. So what is Webb going to also do in the search for life closer to home, our own backyard?
Well, here in our own solar system, we will be looking at everything from Mars on outwards to the farthest we can see. Satellites, comets, asteroids, and the planets themselves. And some of them are really interesting and special because we know they're possible homes of life. What would make a thing a home of life? Well, if it's wet. That's the good clue. So the satellite Europa, which orbits around Jupiter, was discovered by Galileo himself, and we know now that it has an ocean that's covered with ice. There are cracks in the ice where water comes spitting out. NASA are going to send a probe over there to fly through those plumes. We're also going to point over there with the Webb Telescope to see what can see about that atmosphere and those plumes of water. We'll be looking at Titan, which is a satellite of Saturn, which is so big that it has an atmosphere enough to fly a helicopter. And it is cold out there, so that what they have, what is on the surface, is solid ice, and over that are liquid hydrocarbons, which you would use for fuel here in our home. But over there, it's liquid rain, lakes and rivers, and we will be looking at the geology of that before we send the helicopter out there.
So you're on this amazing journey from the very distant early universe all the way to our own solar system, but this has also been a personal journey for you. You've been working on Webb since the very beginning of the mission, is that correct?
I have since '95. We had our first conversation, but people were even dreaming and imagining way before that what we needed. And you could tell even before we launched the Hubble what were the possibilities, and we learned that we would need an infrared telescope that could do things that the Hubble could not do.
Well, John, I've been an admirer of yours for many decades now, and it's an honor to be with you on this part of the mission. So thank you so much for joining us. Best of luck on the launch and the mission ahead.
And thank you for asking all these great questions.
The Hubble Space Telescope delivered profound insights about our place in the cosmos. But perhaps the biggest takeaway from Hubble is that we've only just scratched the surface. Hubble gave us the best ever views of stars and planets forming inside vast, dark clouds of dust. But as soon as we had that data, we were asking new questions that needed better measurements, clearer images. Hubble was also able to capture images from galaxies so far away. Their light took 13 billion years to travel to us. These distant galaxies are just tiny dots in Hubble's images, tantalizing scientists with clues about how the first galaxies form. In order to pursue a better understanding about the earliest days of the universe, we needed to build a better time machine, and that's Webb. So I'm going to be rejoined here by Nicole and Macarena, and this is our chance to talk a bit about building that better time machine. You know, what about the technology of Webb? So there's so many aspects of Webb to start off with, but maybe, again, going back to the theme of infrared. The design of this telescope is so different because we had to use infrared light, heat light. So tell us about some of the challenges of, for example, why does it have to be so cool? Tell us about infrared light in the design.
Right. Well, I think we've heard already just how cool it has to be. It's around or below 50 Kelvin, and that's minus 370 degrees Fahrenheit. Actually, below that is what it operates at. And that's very cold. And the reason we need it so cool is because we don't want the telescope itself to detect itself. Because there's several instruments on board. There's 4 different instruments, and there's some moving parts. And so you need things to be cool, because you want to detect these faint signatures from either an exoplanet atmosphere or faint light from the earliest stars and galaxies. So you just don't want to detect your own telescope.
Now, Macarena, you are the instrument calibration scientist for the coolest instrument.
It is the coolest
on Webb.
yes.
MIRI. So tell us a bit about MIRI and why it needs to be so cold.
So MIRI, it's a really unique instrument, and it's a great example of this collaboration we have in this mission because it's half European, half US. And so MIRI is the only instrument on board that uses the mid-infrared light. And the mid-infrared light is a bit redder, a bit cooler than the near-infrared light. And so because of that, MIRI needs to be colder in order to detect that very faint signal from high-massive galaxies or protoplanetary disks, etc. So because of that, it's the only instrument on board that has a cryocooler. So it is not only the passive cooling from the sun shield, it is active cooling. And it brings it down to about minus 450 Fahrenheit. So it's really extremely cold, a few degrees above the absolute zero.
And we were talking about you don't want the telescope to be so hot that it's basically giving off its own signal, its own radiation, and that leads us to why it needs to be in space, right? So tell us a bit about why do we need to launch this thing into space to see these wavelengths?
Well, again, it kind of goes back to atmospheres because Earth has an atmosphere and there's water in Earth's atmosphere as one example. I mean, there's a lot of other molecules, but basically in the infrared, at the wavelengths that we want to observe some of these stars and planets and galaxies, those wavelengths are actually where Earth's atmosphere is opaque. So with telescopes located on Earth, even at higher mountains where they try to get above the clouds or atmospheres sometimes, there's still residual atmosphere that we're trying to look through and peer through. So in order to see the full infrared wavelength range at a very high sensitivity as well, we need to go to space.
Absolutely. So we talked a bit about some of the power of techniques like spectroscopy. We've heard Dr. John Mather talk about it. So let's go a little bit more into the details of how spectroscopy works and why it's so powerful. Continue.
Oh, sure, yeah, I can keep going. Well, with spectroscopy, we heard, so visible light, again, is it's a rainbow of colors that we don't see naturally. But if you use something like a prism, you can separate out that light and see all the colors from blue to red. But then the infrared is redder than the human eyes can see. But you can still do the same technique where you have spectroscopy tools or instruments like Webb has, all these spectroscopic tools, so that we can break up the infrared light and look at certain colors, if you will, so that we can see certain features that we are looking for, whether it's the right wavelength where a galaxy might be bright or where water is absorbing in an atmosphere.
So Macarena, MIRI has many different capabilities.
It does.
And in fact, it has one that I believe is something different called coronography as well.
Yes.
Tell us a bit about all these ways that we're going to detect different signatures from planets. Tell us about MIRI.
Coronography, it's an amazing technique, but essentially it simulates an eclipse. So when we have a very bright star with planets around, for instance, usually when you take an image, the stars outshines the light of the planet, so you don't see them. But with MIRI and with other instrument NIRCam as well, you can actually block the light of the star, and dim it, and then you see the planets around. And it's really a technique that's going to be very much used and to do, like in this image, direct imaging of planet.
Well, thank you so much. We'll be back to talk to you more with some social media questions. Thank you very much.
Thank you.
NASA and its partners began developing the Webb Telescope years ago, growing from an initial inspiration to a design, then schematics, and finally, reality. What started as a big dream for studying the origins of the universe required best-in-class engineering expertise to transform into something real. Let's take a short look at the very long story about the earliest days of the James Webb Space Telescope.
Before the Hubble Space Telescope even launched, scientists were already discussing what should come next. Ideas for what was then called the Next Generation Space Telescope evolved throughout the 1990s, and by the end of the decade, NASA had a preliminary plan. Construction of the James Webb Space Telescope began in 2004. Beryllium was mined to create the mirror segments, which technicians polished and coated in a thin layer of gold. Meanwhile, engineers designed and built new science instruments in the US, Europe, and Canada. Every step of the way, there were reviews and tests to make sure each part could withstand the rigors of spaceflight. By the early 2010s, the team began bringing individual components together at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It was there that the mirrors and instruments began to coalesce into the grand machine we see today.
We've said before that the James Webb Space Telescope is an incredibly ambitious mission. Big ambitions come with big challenges, and that's certainly been the story of Webb. From the beginning, the design of this observatory has been a balance between the boldest questions scientists have dared to ask and the cutting-edge technology that our best engineers could offer. The design for Webb evolved from earlier ideas of what a telescope could be, another example of the delicate balance between desire versus capability. To get a better understanding not only of the mission's goals, but also the mechanical guts of the observatory itself, I recently got a chance to speak with a pair of engineers who know the anatomy of the Webb Telescope better than just about anyone. I'm here with Keith Parrish, a senior engineer on the Webb mission. And Keith, you brought something to show us today.
Yeah, yes I did. So conceptually, Webb Sunshield is actually quite simple. All we need is 5 tennis court size pieces of this material outstretched to protect the telescope from the sun. So what I have here is an actual sample of that material. This is just Kapton.
It's so light, yeah.
Yeah, it's an industrial, you can buy this and it's commonly used. And what we do is we buy it for Webb, we seam it all together in small pieces, and then we actually coat it with special coatings to give it the what we call the thermal properties we need in orbit. So this one has a nice pink or purplish kind of hue to it, and the reason it's purplish in hue, we use this on the sun side, and we actually put a silicon material on this Kapton, and then we actually put a little bit of a metal in it, and what that metal does is it gives us a nice electrical conductivity. We don't want any surface charging building up, and the other thing is this silicon coating actually drops the temperature of this layer. So, and also it's very durable and can survive, for many, many years in space.
And then this whole thing has to unfold somehow, where we can actually see that behind us.
Exactly right. So if you look at that animation there, unfolding there, so it's actually S-folded up, almost like a fan. We call it S-folding. And once we get it all folded up, we secure it to a structure by actually pinning it for launch. So, a huge shout out to our mechanical engineer and our entire Sunshield team, because they've come up with some really clever ways to secure this for launch, unfold it, fold it, and then, ultimately get it safely deployed in orbit.
That's wonderful. So speaking of unfolding and all these pins that need to release, let's go over here and talk to James Cooper. You're going to show us what's going on there.
Yeah, hi. So I have here an example of a non-explosive actuator. We have 178 of these.
These are all these little pins we're talking about, right?
James Webb, right?
Yeah.
107 of the 178 are the membrane release devices. And we use this type of actuator because it produces a very low shock when it's released. And the animation shows conceptually how it works. We send an electrical signal through either one of our connectors. We use both, but either one of them can cause the release to happen. It melts a small wire inside, and then we have a spring that unwinds and allows 2 halves of a split nut to separate, and then our pin can get extracted. And so in the case of the MRDs, it's a spring-loaded pin that pulls to release the folded membranes. In other places, we would be bolting two pieces of structure together and then releasing them so we can deploy them.
And the sun shield itself has 107 of these?
107 MRDs that all have to work.
Every single one
Every
has to work.
single one has to work. and 178 of this type of device in various configurations around the entire observatory.
Right. Well, if we go over here, we've got something sort of lovely waiting for us, a big gold hexagon. So tell us what we're looking at, a sort of a model here of the mirror segment, right?
Right,
Yeah.
a full-scale, single segment, one of the 18 mirror segments on James Webb. The real ones would be machined out of a single piece of beryllium to the exact curvature we need. And then once we're deployed on orbit, each segment can be individually focused to make it act as a single perfect mirror.
Now that coating, tell us about this gold coating here.
Yeah, so this is coated with a very thin layer of gold. It's only a few hundred atoms thick of gold, and that gold is really good because it gives us a reflective property in the infrared, and that's really what Webb is an infrared telescope, and we need that sun shield exists to cool this entire telescope. So this mirror actually runs about minus 400 degrees Fahrenheit on orbit. If it were warmer than that, the infrared energy coming off of this, that heat energy would swamp our detector system and our instruments. So that entire sun shield exists to cool all 18 of these down. And again, this gold coating is what helps with all that reflectivity to make it perform even better.
Well, that's wonderful. So now you put it all together, and we have a smaller mock-up here, the sun shield, the mirror. Tell us what we're looking at here.
Much smaller. So yeah, this is our entire observatory fully deployed on orbit. And you can see the sun shield here is a large feature. You can see all 5 layers that I talked about earlier. And it's the separation of those 5 layers which lets heat energy escape out to space before it eventually gets to this cold layer. Again, that entire telescope is running minus 400 degrees Fahrenheit, and the way we get it that cold is this side is shaded. The telescope is looking to the deep universe, which is near absolute zero. And then again, this layer here, we've got about a 500 degree temperature drop, so this telescope is also looking at this layer here, which is nice and cold. So that's what lets us harness thermal physics to cool this down to those really, really cold temperatures. Again, you can see our booms, which are fully deployed and stretching this out, and then ultimately all folds up and gets stowed into this structure for launch.
Right, so the membrane release devices would be along the back side of these structures on the forward and the aft side. And we release them in rows so that we can sequentially start to unfold the membrane once those pins are pulled out of the way.
Well, that's wonderful. Thank you so much for joining us, and best of luck on the launch. I'm very excited.
Yeah, thank you.
Okay, let's get a live launch status update from NASA commentator Rob Navius at the launch site. Rob, how are things in Kourou?
Well, thank you, Michelle, and Merry Christmas from the Jupiter Control Center here in Kourou, French Guiana. You are looking live at an Ariane 5 rocket on its launch pad, ready to send the James Webb Space Telescope on the initial phase of its journey. The fueling of the Ariane 5's first and upper stages began before sunrise, and in the last few minutes, mission controllers here in Kourou and at the telescope's control center at the Space Telescope Science Institute in Baltimore conducted polls, with all positions reporting they are go to proceed into the final phase of the countdown. Launch controllers have been monitoring weather conditions throughout the night, keeping tabs on clouds and wind speeds, both at ground level and in the flight path of the Ariane 5, ensuring that all of the precise commit criteria are acceptable for launch. Right now, we have a green board, no issues as the countdown proceeds, no issues again being tracked by the flight control team here in Kourou. By the way, our broadcast today is a collaborative effort between NASA and the European Space Agency. So that's it from now. From the Ariane 5 Mission Control here in Kourou, we'll be back with you soon. For now, let's go back to the Goddard Space Flight Center and Michelle Thaler.
Thank you very much, Rob. So Webb asks big science questions. It demonstrates astounding technology. It inspires and excites people to dream and wonder. And the spark of inspiration is the ignition of creativity. Kids all over the world have a natural affinity for Webb's big pursuits. And now we have a collection of young artists ready to showcase their work.
Hi everyone, I'm Kelly Girardi, and this is Delta V, and we're kicking off the Unfold the Universe Challenge with NASA and the James Webb Space Telescope. NASA is hosting an Unfold the Universe Art Challenge. Use your imagination to share what you believe the Webb Telescope will find.
I believe that the Webb Telescope will see galaxies, stars, planets, the moon, and don't forget our star, the sun.
Up in the sky, really high, it's space.
Ooh, space. Thanks, Greta. Good job.
This is my picture of space.
Hello, my name is Gabriel. I am from Romania. This is how I imagine space.
Hello everyone, good morning. This is a drawing of distant galaxy that can be seen by James Webb Space Telescope.
Hi, my name is Anastasia, and this is what I drew, what I think the telescope will look like, what the telescope will see. I drew the Earth, the Sun, a new planet, a black hole, and stars.
So we've been fielding social media questions from viewers all over the world this morning, and let's take a couple of minutes to share some responses. There's been a couple questions about how long will it take for images to come out, and there's a lot of things that need to happen before the images are coming. So Macarena, why don't you take us through some of that?
Yes, so for the first scientific beautiful images to share with the public, that'll take 6 months. And the reason is because it is, so we launched today, it takes a month to take to the orbit place, to the Lagrange 2 point, and then we have a whole period of cooling down the instruments, aligning the mirrors, and making sure that all the instruments are ready to do science. So the whole process takes 6 months, half a year.
And also all of those 18 segments of mirrors, something needs to happen to get them all working together too, right?
Exactly, because initially you launch with 18 segments and they work separately. So you will take, if you observe one star, you will get 18 little points. So there has to be a process where you take images with NIRCam, which is one of the cameras on board, start moving the mirrors slightly to make them work as a single one, and by the end of this iterative process, you go from 18 points to a very sharp, pristine single point source. So all mirrors act as a single one.
So let's see, we have a question from LV coming in on Twitter. Will Webb be able to enhance detection of comets, asteroids, or meteors that enter our solar system? So that seems we've got a planetary person here.
Sure. Yeah, well, Webb does have a special observing mode where it's able to track these rapidly moving objects, because compared to these distant stars and galaxies, asteroids and comets, they move pretty quickly. And so Webb will be able to do this so that we can study material that's outgassing from them and learn more about what they're made of.
So let's see, there's just so many good questions that we only have time for a few more. So one is from Kristen Rodriguez on Facebook. How long will it take James Webb to reach Lagrange point 2? And you might also just explain what is Lagrange point 2?
So it takes a month. I think it's actually 29 days to get there. And the Lagrange 2 point is this very interesting stable point. So the gravitational pull between the sun and the Earth create this point where it is stable, and you can, as we can see there, Webb can orbit around the L2 point in a very stable orbit, only needs a little bit of corrections once in a while, and it can always have the sun shield protecting the telescope from the radiation of the sun. In a year, in a full year, you can observe any object in the sky, and it's a continuous observation.
Well, thank you very much. We'll hopefully come back to a few more questions later.
Thank you.
So this is a big mission with a cast of thousands to bring it to life all over the world. As we get closer to launch, let's take a brief look at the main locations where Webb took shape on its journey to space.
Inside the massive high bay clean room at NASA's Goddard Space Flight Center, engineers assembled the 18 gold-covered mirror segments into the backplane of the telescope and integrated the 4 science instruments contributed by international partners. To simulate the harsh environment of launch, they went through vibration tests and acoustic tests. And to simulate a space environment, the instruments endured cryogenic testing in a large thermal vacuum chamber. But it wasn't large enough to hold both the instruments and the mirrors, so the telescope boarded a plane to Houston, Texas, to visit the only thermal vacuum chamber in the world big enough to fit the entire assembly. Chamber A at the Johnson Space Center was originally built to test the Apollo spacecraft, and half a century later, it provided a grueling 100-day test for the Webb Telescope. Next, the telescope traveled to Northrop Grumman's facilities in Redondo Beach, California to meet up with its other half, the Sunshield and spacecraft bus. Fully assembled at last, the entire observatory went through yet more tests, many focused on making sure the spacecraft could properly fold up for launch and unfold in space. Then in September 2021, Webb caught a ride on a specialized cargo ship and set out on a 16-day voyage to the European Space Agency's spaceport in Kourou, French Guiana. According to its travel itinerary, that's Webb's last port of call on Earth.
Once Webb gets into space, we're going to have some exciting things to tell you about what happens next, from its extraordinary engineering to the thrilling scientific adventure it's about to enable us to undertake. But launch comes first. And for that, I'm going to turn it over to Katie Haswell, our host at the launch site, and one of NASA's most recognizable voices, launch commentator Rob Navis. It's all yours, Katie.